much, Dirk. Hello, everyone. Thank you very much for joining. As Dirk introduced, we'll be presenting on Supreme technology. This is the next generation of plasma thrusters for space missions. My name's Marcus Collier-Wright. I'm the co-founder and CTO of Neutron Star Systems. I'm here today with Manuel, who's also my co-founder and the CEO of the company. So just to give a brief outline of what I'll talk about today, I'll give you a quick background of the company and where we've come from. I'll then introduce our main propulsion technology, applied field magnetoplasma thrusters. I'll introduce to you high temperature superconductors and how the combination of these two technologies gets us to Supreme technology. I'll introduce the Supreme technology and link it to our vision and our business case, and then our roadmap for how we plan to implement this vision, and briefly describe some of the traction that we've achieved. So Neutron Star Systems is a startup based in Germany, in Cologne, and our main focus is building disruptive electric propulsion systems based on high temperature superconductors with a key focus for high power space missions. Now we are coming and we've been formed with the support of 3 entities. In the pink we have IRS, the Institute of Space Systems at the University of Stuttgart, who have a very long heritage in research and development of electric propulsion systems for spacecraft, as well as extensive testing facilities for electric propulsion. We have Absolute System, a French SME, who are an expert on cryogenics with ESA qualified facilities for assembly and integration of spacecraft components, and their instruments have flown on several ESA missions. And finally, we have PI Solutions. This is Manuel's consulting company, also based here in Cologne, which brings over 10 years of business innovation heritage and an expertise on superconductors. To give a little bit more background, our main background is formed from 2 consortia which were built in the framework of European Union funding. The first one was the Supreme Consortium, the stand for Superconductor-Based Readiness Enhanced Magnetoplasma Electric Propulsion, but I'll just call it Supreme. This was formed with PI Solutions as the coordinator, with the support as well of IRS and Absolute System, as well as our partner Teva from Munich, who is the largest producer of superconductors in Europe, and also the DLR, Airbus, and in total 11 SMEs and research institutes from around Europe. So together, this consortium put together the articulation and concept of the Supreme technology and submitted a proposal for funding, which unfortunately was not granted. The second consortium is the MIST consortium. This is Magnetohydrodynamic Enhanced Entry System for Space Transportation. And in this consortium, it was also an application of superconductor technology to spacecraft, this time for a re-entry shielding system to generate a magnetic field and shield the spacecraft as it re-enters the Earth's atmosphere. And we're in this consortium as Neutron Star Systems, alongside our main partners Teva, IRS, and Absolute System, as well as 6 other leading universities and research institutes from around Europe. And this consortium was successfully funded by the EU in February. We received a total of 3.4 million euros for building a demonstrator for a superconducting magnet, and the project will begin in October. I'd like to introduce to you briefly our team in the company of Neutron Star Systems. You've met Manuel and myself, and with the rest of the management team between us, we have over 80 years of experience in industry. We have a wide range of different disciplines and experience in example areas like high temperature superconductors, spacecraft systems engineering, electric propulsion, and putting things in space. So Dave is our head of engineering. He's put several pieces of equipment in space, including previous 2 electric propulsion systems. And Professor Georg Herdrich from the University of Stuttgart is our expert on the MPD technology. He's the leading authority on this technology in Europe and has overseen the production and experimental testing of the most advanced prototype anywhere in the world. In addition, we have a really strong, diverse support team, which comes from a lot of backgrounds, 4 different nationalities, and with a lot of different disciplines. And they give us the flexibility and the versatility and the determination we need to overcome the challenges with which we are faced as a company. So now I'm going to start to get a little bit into the technical details of what we're doing. And the first part I'm going to introduce to you is spacecraft propulsion. And with spacecraft propulsion, we have 2 main categories. We have chemical propulsion and we have electric propulsion. The chemical propulsion is what you typically see with a rocket. You're burning the fuel and using that to generate thrust. Whereas with electric propulsion, the power source comes from the electricity supply, and this is what we use to generate the thrust. And the main difference between the 2 is how efficient they are. And the best way to illustrate this is with an example. If we take, for example, a 6-ton satellite, this can be, for example, a communication satellite. If it has a chemical propulsion system on board, half of this mass would have to be fuel just to get the satellite to where it needs to be. So within a few days of your mission, half of the mass is already gone. It's been used to transport the satellite, and it's essentially wasted space. When you consider that for launching every kilogram into space can cost around 15,000 euros, then this is a very big waste of money, so to speak. With electric propulsion, we can significantly reduce the amount of fuel needed for a satellite. So in this example, we go down to 1 ton, and this means that either we can have a much bigger payload, we can have more powerful computational power, we can have more powerful antennas, for example, greater communication capabilities, or we can bring down the mass of the satellite and save a lot of money on launch costs. To go into a bit more detail on the propulsion technologies, again with the chemical, like I mentioned, we are burning the fuel to produce thrust. This has a lot of benefits. It's relatively simple. It's got a lot of flexibility in terms of which propellants we can use, and a lot of flight heritage. These chemical systems have flown in space for over 60 years. Unfortunately, their specific impulse is low, and specific impulse is a measure of how efficiently the fuel is used. So with a low specific impulse, you need to use a lot of fuel. And also controlling the propellant is quite complicated. Then we have electrostatic thrusters. This is a type of electric propulsion where we ionize a gas and accelerate the ions using electrostatic methods. So here we have a high specific impulse. They use a lot less fuel, and they also have high thrust efficiency, and they've been flying now for several years. However, the operation is quite complicated. They rely on xenon, which is very expensive and rare as a propellant, and they do not scale well to higher powers, so they're only suitable for the current size of spacecraft. Finally, we have electromagnetic thrusters. These are also a type of electric propulsion system. Also, we form a plasma and accelerator, but this time with electromagnetic means, and this gives us some more benefits. Again, we have a high specific impulse, but we're throttleable. There's a much larger range of operational conditions, and you can use a lot larger range of propellants, including propellants which are much cheaper and much more available. The problem is that to date they've been limited by conventional technologies, and as such they don't have very much flight heritage. What we are working on at Neutron Star Systems is an electromagnetic thruster called the Applied Field Magnetoplasma Thruster. This is formed of 2 electrodes, an anode and a cathode, which are separated by an electrical insulator. We feed an electric current between the 2 electrodes, and this creates an electric field between them. And then we feed the propellant in between the cathode and the anode, and when it goes to this electric field, it becomes ionized and forms a plasma. We now have a current running from the anode to the cathode through the plasma, and this induces a magnetic field in the azimuthal direction around the central axis. And this is where we have our first acceleration mechanism. The combination of this magnetic field and the radial discharge current causes what we call the self-induced acceleration. Now, with an applied field magnetoplasma dynamic thruster, we apply an external field using a coil, and this creates then an actual magnetic field, which you see here in pink. So then we get 2 further acceleration mechanisms. We have the azimuthal component of the discharge current and the actual component of the magnetic field, and these cause a Hall acceleration. And finally, we have the interaction of the radial component of the discharge current and the actual component of the magnetic field, and this causes what we call a swirl acceleration. Further to this, we have a 4th acceleration mechanism caused by the thermal expansion of the hot plasma and the hot gases. So this is a very interesting technology, and because of this, it's seen over 60 years of research heritage. And this was actually initiated in the early 1960s right here in Germany, in Stuttgart, who built the first prototypes. Then the USA built several prototypes over the 1960s, and also Japan started to get involved in the 1970s and 80s, and they actually flew the first flight mission of an AFMPD thruster. This was an experimental mission, but then this made NASA to do some further research in the 1990s, where Russia also produced some thrusters, as did Japan, and in total then there were 3 flight experiments of this thruster. After 1996, there was a downturn in the interest of the technology until 2010, when 3 new prototypes were built, 1 in Italy, 1 here in Germany, and 1 in Japan. And the research has since seen a lot more interest, and there's been more prototypes built, again by the Japanese, here in Stuttgart, and now also by the Chinese. I'm going to focus on this prototype from 2016, built in Stuttgart, which is the most advanced prototype built in the world. and this is called the Sx3 thruster. It's a 100 kilowatt class thruster, which in terms of spacecraft is very high power. However, the mass of the thruster is only 13 kilograms, and this for 100 kilowatts is extremely lightweight. So this is just showing how suitable this technology is for high power applications. The problem is that it requires the electromagnet, which is made out of copper at the moment, is extremely large. It weighs 150 kilograms and consumes nearly 300 kilowatts of power. And this is really the obstacle preventing it going into space. Having said that, there's been some very promising performances achieved by the Sx3 thruster. We have these photos here of it in operation, courtesy of the University of Stuttgart. And it has achieved up to 62% thrust efficiency, which is comparable with the status quo of technologies which are currently flying in space. And what I wanted to show you with this slide was the impact of the magnetic field. So I've taken two data points, one at 100 milliteslas and one at 400 milliteslas. And the one with the higher magnetic field has a much higher efficiency. Not only this, but we operate at a much higher voltage and therefore a lower current, and this means that the lifetime of the thruster is greatly increased. What does this mean in the parameters which we care about? It means we have a high specific impulse, it's more efficient, and we have a higher thrust. We can get to where we want to go quicker. So what we have is a technology which is very interesting, has a lot of potential, but has been held back by technologies which are too heavy, too power hungry, and which need to generate a high magnetic field. And the solution for this problem is high temperature superconductors. What we have on this slide is a graph showing the development of superconductor technology in the last 100 years. And until the 1980s, all superconductors had to be cooled to extremely low temperatures below 20 Kelvin in order to operate. And this is very challenging from a cooling perspective. Then since the 1980s and the 90s, there's been a lot of research and a lot of new materials discovered which have much higher critical temperatures, above 80 Kelvin, above the boiling point of liquid nitrogen. And this is important because they will be superconducting at these temperatures, and the requirements and the demands on the cryogenic system are significantly reduced, which make them much more suitable for space applications. Not only this, but this technology has now been commercialized, is now very industrially mature. This is a photo from our partners in Munich, TEWA, who have a modular process for building and manufacturing superconducting tape. It uses several processes such as physical vapor deposition and electron beam evaporation. And this procedure is now achieved economies of scale. It's a cost-efficient process. It provides a high yield, high quality consistency, and this is now a fully commercialized product, which means that these high temperature superconductor tapes are now available at very reasonable costs and in commercial quantities. And because they're so light and because they have zero power losses, this makes them very suitable for space applications. Not just in electric propulsion, but also for other applications. You can use them, for example, for re-entry shielding, as in the MIST project, which we're working on, as well as power transmission lines, radiation shielding for astronauts, and also superconducting magnetic energy storage. But today we're going to focus on the application of an electric propulsion system and the combination of superconductors and AFMPD, which we call SUPREME. Now, the SUPREME concept is built on 5 main subsystems. We have a propellant supply and we have a power processing unit. These supply the propellant and the electricity to the thruster. They're connected to the discharge unit where the propellant is ionized. And we have the applied field module, which contains the magnetic coil that provides the magnetic field for the propellant acceleration. Finally, we also have a thermal management system, which is very important to keep all of the components operating at the right temperature. Now, what is the impact of replacing the copper coil with a superconducting coil? Well, we can reduce the magnet mass by a factor of 4. We can reduce its power consumption by a factor of 300, and we can increase the magnetic field strength by 4 times, which means we have an increased performance and an increased lifetime. Here are some of the technical parameters of the thruster. We have a very wide range of operation, very scalable in terms of power, in terms of specific impulses, and in terms of thrust, which allows it to be applied to several different mission scenarios. I'm just going to go into a little bit more detail about some of the specific requirements of the different subsystems. So firstly, with the superconducting coil, we are aiming for a coil which can generate 1.5 Teslas of magnetic field strength at a critical temperature of 50 Kelvin. And other things we need to consider are quench protection to avoid it, make sure it doesn't get damaged if the current has to escape. as well as looking at current leads and flux pumps as possible ways for loading the coil with electricity. In terms of the cryogenic system, we're looking for requirements of 40 watts of heat removal at 50 Kelvin, and for this we've identified the reverse turbo Brayton cycle as the most suitable cryogenic system. The requirements in terms of the system integration is a power draw of less than 800 watts and low vibration operations that we can use it in space. The thermal management subsystem is one of the key subsystems, mainly driven by the challenge of insulating the high temperature superconductor coil, which can be at 50 Kelvin, from the plasma discharge, which can reach up to 2000 Kelvin. So for this, we're looking at some high temperature resistance refractory materials and a multi-material thermal management architecture, considering aerogels and multi-layer insulation. Finally, for the anode, we have several requirements, which are mainly electrical conductivity, high temperature resistance, and also a low work function and sputtering resistance. And these two are critical in order to minimize the erosion of the anode, increase the thruster lifetime, and improve its efficiency. So I would like to give you a little bit of a comparison of this technology with existing technologies for electric propulsion. And to do this, we take two metrics. We take specific impulse and we take thrust. Hall effect thrusters are a status quo technology which provide a relatively high thrust but at a low specific impulse. We have gridded iron thrusters, on the other hand, which provide a high specific impulse but at a low thrust. Both of these technologies are very much fixed to their specific area of the graph. With Supreme, we can offer high specific impulse, we can offer high thrust, and we can offer operation at the most suitable point for the specific needs of the customer. To give a brief overview of the competing companies in the electric propulsion landscape around the world, this is a list of companies working on mid to high power electric propulsion. You see most of them are working on the status quo technologies. However, for gridded iron thrusters, these are very hard to scale beyond 10 kilowatts. And for Hall effect thrusters, beyond 20 kilowatts, it's also very difficult to scale. And this is what you can see with the power ranges of each company. Aerojet Rocketdyne in the USA are working on an ultra high power Hall effect thruster, but at this power class, our system is going to be up to 4 times lighter than theirs. Ad Astra Rocket in the USA are working on another technology called basieren, but this is limited only for high power applications. And here at Neutron Star Systems, we can actually access the widest range of power classes of any company between 1 and 1000 kilowatts. So just to summarize the competitive advantages I've been speaking about in the last few minutes. Firstly, we have a high propellant flexibility. We can operate on alternative propellants like argon and ammonia, which are 2 orders of magnitude cheaper than the status quo xenon. And this also opens up new opportunities for hybrid chemical electric propulsion systems. The technology is simple and robust, and is backed by over 60 years of research heritage in 6 different countries around the world. The technology is highly scalable. We can scale up to higher power classes with minimal mass and volume penalties, and we have a wider range of scalability than any of our competitors. And the technology is highly throttleable. We can operate it over a wide range of conditions, making us suitable to several mission applications and allowing us to optimize thruster performance for individual orbital transfers. To put this throttleability into a little bit more context, I have a graph here which is showing the specific impulse on the x-axis and the thrust on the y-axis. In general, we have a trade-off between the two. And what you see with the red dots on the left side is operating points for Hall effect thrusters, and with the blue dots in the middle, operating points for gridded iron thrusters. And these are fairly closely grouped within a specific set of operating ranges. The blue shaded area is what we can access with Supreme. And this shows just how wide an operational area we have, making us applicable to several different mission scenarios. And this is what forms the basis of our vision. In the near term, we see that we have applications for small satellites and constellations, and for geocommunication satellite platforms, as well as for satellite servicing vehicles for near-Earth applications like debris removal and decommissioning, orbit raising of satellites, satellite refueling, and satellite maintenance. Looking further ahead to the midterm, we see a lot of applications in the lunar-based space economy, starting with lunar gateway logistics, also with lunar servicing and cargo transfers from the Earth to the Moon. And looking even further ahead, there's applications for Mars missions, like Mars cargo transfers, crewed Mars missions, and the establishment of a Mars gateway, as well as future markets such as asteroid mining and science and exploration missions. So while we have a short-term market plans, our real vision is to enable this next generation of space missions with our technology. To put this into a little bit of context, we've evaluated the opportunity which is at stake here. We see all of these missions entering the market on regular intervals, driven primarily by the introduction of our thruster technology. And we're predicting that by 2039, we can access over 500 million euros per year in revenue. To give an example of the business case and why our technology can do this, we've run several studies. We've taken reference missions, which are considering status quo current technologies, and replaced it with the SUPREME thruster. And we see savings based on reduced subsystem masses, increased efficiencies, and reduced propellant costs. So for a geocommunication satellite, we can save up to 10 million euros. For DLR Jupiter Moons mission, up to 20 million euros. For a small satellite constellation, up to 30 million euros. And when you get to the higher power missions, the savings get even larger. 90 million euros for a moon cargo mission, and 320 million euros for Mars cargo. How we're going to take advantage of this business case is the business model. Our main activity is to develop the SUPREME technology and secure the IPR. And we will combine this with a cyber-physical platform, which will consist of artificial intelligence, computational powers, and plasma simulation and material simulation data, which will allow us to perform advanced and rapid prototyping and qualification of new thruster power classes. And this will enable us to access our main revenue streams, which is selling propulsion systems for 3 main market segments, starting first with near-Earth applications, in the midterm with lunar missions, and in the far term for Mars and deep space missions. And this will be supported by secondary revenue streams coming from the application of our superconductor-based subsystems to other electric propulsion technologies and to other spacecraft subsystems, as well as the licensing of intellectual property rights. And we can transfer this technology to aviation and naval markets as well. In order to access these first 3 product market segments, we have an initial product line consisting of the 1 kilowatt class, which will use permanent magnets rather than superconductors, first applicable to small sats and constellations, and for use in hybrid propulsion systems. We'll then have a 5 kilowatt class, which will be the first thruster class using superconductors. This will be our proof of concept demonstrator. We've chosen this because it is comparable to the industry standard 5 kilowatt thruster class and can be used on communication satellites. And then we'll have the 20 kilowatt class, which will allow for the first advanced missions, such as extended geosatellites, advanced science missions, and satellite servicing applications. To give a brief overview of the company's structure and how we will execute this business model, we have our HQ here in Cologne, in Germany, and this will be the center of competence for developing the discharge unit, the thermal management, and the propellant control system. We're also planning to open subsystem assembly and integration facilities here, and we will have our thruster testing and verification facilities at the University of Stuttgart. Since April, we have incorporated a new office of the company in the UK called NSS UK Limited, and we're doing this to tap into the big knowledge and the vast experience on the areas of superconducting coils, cryogenics, and power electronics. And we also envision the opening of a branch in Luxembourg in the next few months, where we'll work with our main partner, Spark Industries, on the development of plasma simulation tools for our cyber physical platform and the optimization of the thruster development. So I'd like to just give you an overview of where we're planning to go in the next 20 years. We're building on significant heritage and significant development in MPD technology and high temperature superconductor coils. And at the moment in 2020, we're at TRL4. We plan to get to TRL6 with our thruster by 2023 through the production of an engineering model, aiming for an in-orbit demonstration by 2025. And after this, we will pursue the full commercialization of the technology, starting with small sats and constellations and next generation communication satellites, before moving into future mission applications such as satellite servicing, cargo transfers, and crewed Mars missions. I'd like to finish off by just giving you an overview of some of the traction that we've achieved in the last few months. So we went to the New Space Business Plan competition in Austin, Texas last November, where we were given the Audience Choice Award. We were runner-up at the Startup Space competition in Washington, DC in March this year. We're a top 3 finalist of the OHB Challenge at the Inner Space Masters right here in Germany. We've been named as one of ESA's top 50 startups of the year. And we're also a finalist at the Fit for Start Accelerator program taking place in Luxembourg later this year. And of course, our main achievement being part of the MISS project, which has received 3.4 million euros in funding from the European Union. We've had a lot of discussions with customers, with major primes, here in Europe, Airbus, OHB, and ESA, as well as major customers in the USA, such as Northrop Grumman and Sierra Nevada Corporation. The feedback that we have received is that what we're doing is very important, very interesting, and there's a big demand for the technology. Based on this traction, we really believe that the time is now to push this technology and to develop it. We are always looking for new people to work with who can help us to pursue our technical challenges and aid in our development. So if you're interested to work with us and to find out more about what we're doing, please get in touch with us. Thank you very much for listening, and we'll be happy to take any questions you have.
Thank you. Thank you, Marcus.
Oh, thank you from my side too. We've got the first question in the chat from Mark Gorick. There's someone, so I want to suggest to read it, and you can answer to that. I remember you were thinking about using technology from fusion research. For example, HTS Croco from KIT. Is that right?
This is
Or
KIT, Cosgrove Institute of Technology. Yeah. Yes, so Mark, I believe we spoke a few months ago about the Eurofusion program. Fusion energy is one of the major examples of high temperature superconductors being applied in terrestrial environments, and you know, we have several partners who we're in contact with from this area, and we're also in close contact with KIT. They're part of the consortium for MIST, and they're working on superconductors there, and we have some other projects we are looking at with them as well. So certainly a lot of the technology transfer from fusion research is very important for us. Another part of it being the radiation resistance. Especially in space, there's a lot of radiation exposure, both near Earth and in interplanetary space from different sources, such as cosmic gamma rays and the solar wind. So especially from the fusion industry, one thing which we can certainly look to take is how to protect the coils from being impacted by radiation.
Thank you. Other questions? Yeah, there's another one. Can you go more into detail of already available and tested hardware?
Yes. The current status quo of the technology is 4. So when we want to address this question, we need to look at the TRL of the different components. So in case of the discharge units, there have been already prototypes put in place, mostly at the University of Stuttgart. And the status quo is relatively high. If we talk about the applied field module, we have for superconducting coils a very high degree of maturity, since they are used in other applications, terrestrial applications, and have been produced largely in commercial quantities. So in that sense, the validation that it needs to be done is the integration of the cryogenics and the superconductor, and tested in a relevant environment, which is in this case vacuum. So for that, there have been also experiments conducted at KIT, and the technological challenge for that are considered, in my opinion, not so high. If we look, for example, at propellant technologies, propellant flow controllers, you will have a very high status quo, a very high TRL, especially on xenon flow controllers. For argon, there needs to be some qualification, which is the case of our propellant, but the technology is pretty much off the shelf. In terms of the thermal insulation systems, that's one of the main challenges, and for that, we're bringing innovative approach to build the corresponding prototypes.
Okay, and what is the biggest obstacle in realizing the technology up to the product level, apart from the necessary investments?
Well, you have to provide a turnkey solution. So you have also the case of the plasma simulation. And this is extremely important because plasma simulation for MPDs hasn't been developed since quite a lot of time. So when we compare the status quo of plasma simulation for MPDs with the status quo of plasma simulation for electrostatic thrusters, for example, they are more advanced. The code requirements for plasma simulation is particle in cell, 3D code, and the simulation of the physics phenomena has to be first written and then validated with experimental data. And that is also one of the biggest challenges. The other challenge we see is the power supply, because we need, for high power missions, it's also necessary to have conventional technologies for such high powers, and there are some limitations. So that's why we're working, for example, with Crisol AG, is a Swiss company, and they have technology for ultra lightweight solar deployable arrays. The problem here is that the TRL of that technology is much lower than the propulsion technology. So here, both together bring a strong combination for high power missions at a very low cost and with very low masses. But there is a gap on at TRL level between one technology and the other one. That's the last. And the third challenge is in my opinion, is the lack of coherence at policy level. And here is where this is something that we have been addressing in different fora. For example, the NATO Joint Air and Space Power Conference. And in the case of the political level, what we see here is that the technology have a strong demand and a strong importance in the FISI group. And this is a group made out of UK, United States, Australia, New Zealand, and Canada. And there have been little coordination between Germany at that level regarding the evaluation of the technology together with the USA and, for example, the United Kingdom, which we have been talking for quite a while since now. So what we see there is that the challenge at political level is we need to understand what we're able to achieve at a mission level with this technology within Germany, and how this is going to be suitable to support the activities of primes and system integrators such as OHB, which is also one of our partners and has given us a technology endorsement, or Airbus, who has done the same. So yeah, these are the main challenges. Thank you. Okay.
So Jason Norman wrote, thanks for the presentation. It's a fascinating project. You mentioned the need to secure IPR. Is there any existing IP which would potentially limit your freedom to operate? And are there any problems you anticipate for accessing it?
I would prefer not to answer that question.
Okay.
I will prefer, I mean, if there is a further question about it, then we can do it offline, but not via
mail. So I think after the presentation, I will send the slides to any to all participants so they can get into contact with you.
Yeah.
Okay. So the next question, in terms of thermal control, you mentioned as a critical part. Is it at all about radiating heat from the spacecraft, or also isolating the maintaining low temperature gradients?
I mean, it is both. And I think that Marcus has a better answer to that question than myself. So Marcus, please.
Yeah, as Manuel said, it's both. You know, we need to make the considerations of the thermal challenges on both the propulsion system and the spacecraft level. In terms of the propulsion system, the major challenge and the main driving requirement is the insulation of the coils at the cryogenic temperature from the hot plasma plume. So here it's important that we make sure that the coil is not going above its critical temperature, because then it becomes not superconducting anymore. This can damage the coil and potentially prevent operation of the thruster any further. However, on a spacecraft level, we need to radiate heat away from the thruster system, but also from the spacecraft. But you also need to consider all of the incoming heat sources. People have this idea that space is cold, which it of course is, but especially when you're near the Earth, there's significant thermal incoming from the planet itself and from the sun, and also from all the instrumentation on board. Especially when we have a cryogenic system on board, not only for the thruster, but also, for example, for propellant storage or for any other subsystems such as power processing or radiation shielding, then this is a fairly complicated thermal environment which needs to be strongly analyzed. Manuel mentioned one of our partners is OHB, and we're currently working with them on a project to address some of these questions.
Okay, then there's a second part of this question. Do you think there will be COTS solutions for this in the maybe far future?
What does it mean by COTS?
COTS is commercial off the shelf.
Okay.
This is it's a very interesting question, because one of the characteristics from new space, certainly in the last years, is the development of commercial off the shelf components, which have really reduced the access to space, because now products can be produced in series and at lower cost. We believe that we can get to this point as well. This is where the importance of the cyber physical platform and all the simulation capabilities comes into it. And this will allow us to have a very flexible manufacturing and design process, and eventually provide as well standard thruster power classes which can be integrated to different mission applications with minimal customization.
I would like to add something to that, Dirk, and this is, for example, one of the most critical components in the thruster, which is the applied field module, consists of two further components, which is the HTS coil and the cryogenics. You can never have, this will strongly change depending on the configuration that you want to give to the magnetic field, because you have a lot of flexibility in the design. So what we're building is, the basic footprints for an off-the-shelf product. But what we're offering on top of that is also the design flexibility and the prototyping capability to bring the product into a fast time to market. Just because you already have the basic blocks of technology, and then you need to do the necessary modifications depending of the type of platform that you are going to apply the thruster. Just to give you an example, economies of scales in terms of missions. If you, for example, launch a geocommunication satellite, you need a clustering of at least 4 thrusters. 2 thrusters that are going to be for redundancy reasons, and another 2 thrusters for doing maneuvers in one direction or the other one. So one communication geosatellite is 4 thrusters, and you have to consider that you have a annual demand or an annual volume of more or less 20 geosatellite missions per year. So it's a rather small market, but it's a market that is going to grow. It's going to grow because the LEO market, the low Earth orbit market, is now going to get more populated. So communication satellites, which are rather large investments and a lot of capital, are going to be always sent to geostationary orbits. On top of that, probably the support of networks of institutions like defense or government are going to be also built in constellation from the geostationary orbit. So that's why we see there is a market demand to generate economies of scale that lead to COTS.
Okay. So the next question is, you mentioned technology application also at some point to aviation. Would the thruster be able to breathe air?
No. The technology transfer to aviation is based on the fact that we can use or apply the superconductors for doing DC busbar for transmission, for power transmission in electric propulsion for airplanes. This is rather an old approach and is used in the UK for large plane passengers. Companies like Rolls-Royce have been conducting a superconducting program since more than 10 years. And that's the status quo of the technology at the moment. So by developing the different subsystems that we need for our propulsion systems in space, we can then transfer the technology also to applications like transmission busbars in aviations, or also the development of or the production of power appliances, such as superconducting fault current limiters, transformers, and probably even superconducting magnetic energy storage. All of these power appliances have been considered in the architecturing of electric propulsion systems for planes. And depending on the class of plane that we're talking about, makes sense to use them or not. Just give you an example corresponding to conventional technologies. An Airbus 320 needs 40 megawatts of power for taking off. So you need to consider larger planes that are totally electric. The cabling that you will need is not going to allow the plane to take off. That's why superconductors are the unique key to enable full electric propulsion systems for aviation.
Okay, so this is the perfect link for the next question. You mentioned the gain in payload weight compared to the chemical propulsion systems. But did you compare the weight of the propulsion systems? I can imagine that the strong magnets, coils, maybe also the shielding is not lightweight in a classical manner.
Okay.
I'll take this one.
Marcus, you go for it, please.
I spent a lot of time on these studies. Yes, indeed, we have compared the systems, and I think the best way to answer the question is to take the example of the 6-ton satellite, which I gave at the beginning. For such a satellite, we might expect 4 electric propulsion thrusters, which each weigh about 20 kilograms. So in total, that would be 80 kilos for the propulsion system, and you save 2 tons of fuel. in terms of the chemical propulsion system, it's still very similar because you have a lot of the same requirements in terms of propellant control. You still have pipes, you still have a nozzle, you still have cooling systems for that nozzle and for the other parts of the chemical system. So even if the chemical systems on their own may be slightly lighter, you have to look at it from the spacecraft point of view, where you might save a few kilograms, but in terms of the difference of propellant, it's tons. That's where we have the saving.
So in other words, you couldn't compare both technologies, I will say, because at the end of the day, the specifications for the applications are different. You need in-space, for the in-space propulsion, you will have payloads that are going to be at the largest with the current status quo up to 12 tons, you see? And that's the maximum that size of satellites that have been sent so far to space. And the use of chemical propulsion systems for this kind of satellites will bring a significant mass addition to the spacecraft when compared, for example, with electric propulsion systems, where you're going to have at least 3 tons, as Marcus previously mentioned, or 2 tons available or space for your satellite. So I don't think too much a conflict there in terms of lightweight.
And there's another question. How do you consider to get artificial intelligence involved in the cyber-physical platform?
Yes, this is the following. We need to coordinate. We need to coordinate a database architecture which is based on inputs with different from different sources. And AI is especially ideal to help building the interfaces for the different sources or the different types of data to exchange. So the use that we see particular is how do we combine, for example, experimental data obtained in a vacuum chamber, and how we improve the numerical rebuilding of that experimental data with the existing codes. And this is a very large process. It takes a lot of iterations, etc. And I think that this is, for example, one of the major uses of AI. And when you consider also other variables like thermal simulations or magnetic field topology, that is also considered. You have data inputs, which are coming from 3 different sources, all of simulation, all including codes, and that needs to be integrated in order to be able to make a digital twin of the thruster, and then that says, and then indeed iterate on the design and potential testing.
Okay. Any further questions? Okay, that's the next question. Wait. Does HTS material or cryogenic systems, fluidic N2, react on space radiation? In other words, do these subsystems require respective shielding?
That's a very interesting question. And to the question of the nitrogen is an inert gas. I don't think that this is, I mean, I need to check this out, whether some charger particles can do something on nitrogen. I'm not really the expert on that, but what I can say here is that in the case of the cryogenic systems that we use for that technology, we are making use of an existing technology that have been, or system that have been already proven in space. And this is not using hydrogen, this is using helium. And it's a closed loop system using turbobrayton technology. And this system is quite efficient. And I do not think that helium will have a special sensitivity towards cosmic radiation. However, I'm willing to look at this. This is a really nice question. Thanks a lot. Marcus, I don't know if you want to add something to that.
This is indeed something which we need to double check, but considering the previous flight heritage, we don't at the moment have concerns about that. In terms of the superconducting material, of course, the radiation can be an issue, and it can be damaging if it's not dealt with properly. Here, there's several different approaches in terms of sort of passive approaches for protecting the superconductor if there's some damage, or if there's it raises above its critical temperature. And we also hope that we can take some technology transfer from the fusion industries, where you have superconductors in close proximity to nuclear fusion processes, which are also giving off significant radiation. So there's certainly a solution there.
Okay, and could you also use liquid nitrogen for the HDS?
Yes, you can.
Okay.
That's the way, especially in cabling applications for high voltage or medium voltage. The systems, the cooling systems used are in use are considered using nitrogen.
I'll just add to that. It may seem odd that we're talking about nitrogen and we also talk about 50 Kelvin in the presentation. When we have a coil which is generating a strong magnetic field, as in the propulsion system or in the radiation shielding system, then we need to operate at a lower temperature because the superconductor is more sensitive to the temperature in the presence of a magnetic field. So for these applications, we won't be able to use liquid nitrogen as the temperature is too low. Instead, we would be looking at helium. However, for some other applications, such as the power processing and the propellant storage, we can certainly use liquid nitrogen.
More questions? Dirk, do you have any question? I see your picture.
You see my picture? Yes, I've got a last question. You've mentioned so many subsystems, and if one of the participants is developing such of a component or a subsystem, are you open for cooperation? And which component would you say would be most important or most interesting for you for further cooperation?
You have to unmute yourself, Manuel.
Absolutely. We have conversations ongoing. We have been since 3 years doing this project. So we have a quite good understanding of the different technologies available that we need to do our job. But I'm always welcome to have a discussion with whoever have an idea how to support us of any technology. My experience in the last 10 years in the state of North Rhine-Westphalia and doing innovation and working with institutions such as Fraunhofer Institute, then small, medium companies in the Dortmund area for plasma atmospheric spraying and thermal spraying processes, is that the technological park existing in NMW at the, let's say, component level is quite good, and we have a lot of innovative companies here, but I don't know them all. And so I would be really happy to receive any inquiry, and please feel free to contact me through email.
Yeah,
Perfect.
I don't want to limit it to North Rhine-Westphalia, because the
Of course
participants
not.
come from whole Europe here,
Of course,
from different countries.
No, I mean, Marcus mentioned this at the beginning, and the problem with space technology is a very fragmented, sector. So you will find very small companies in Spain, Italy, Greece, you know, that are doing really unique things for space, and that are extremely needed because no one else can. So the combination of all of the technologies that you need for the different for the different components is one of the most important challenges also that we have. And in that sense, I always look over the Randteller, the Tellerrand. So I can always look a little bit besides my own window. So yeah. This is really nice. Thank you.
Okay, you spoke about Europe, but what about Japan? Are you also in contact with and cooperating with partners in Japan, or are they rather your competitors?
Japan, no, absolutely. We have a very, not very strong, but I mean, at academic level, there are, let's say, two superpowers, if you want to call it like that, in MPD and MPD thrusters. One of them is Germany, and the other one is Japan, because they have been the only countries that have been actively pursuing development of the technology and also investing. In Europe, it has been a combined effort, because ESA this technology is anchored in the technology roadmap for high-powered electric propulsion in Europe and ESA. And in Germany, we don't have too much funding or too much attention at the moment, but in Japan, the relationships at academic level are really good. And we know the different universities working and different technologies. The only problem with Japan is that's something you need support with for, Dirk. And it needs also some kind of stimulus and mediation of third parties, because it's, as a small medium enterprise, it's very difficult to cooperate with Japan, but I would love to. They have Japan is one of the leading countries on superconductor technology.
Okay,
so,
the question was from Georg Löhr, and I think he's a brilliant contact for you to Japan, I think.
okay. Thanks a lot. Thanks a lot. Because
Okay.
this is really like, yeah, they're a key strategic partner, could be. But then you have, the culture of the language barrier. Yeah.
Ah, okay. He already wrote he would like to help to mediate. So I think you should get into contact afterwards. There's another question. And what is your next step in the technology development? What is your next step at NSS?
That's a good question. We have three ways of operation. I mean, we are now applying to the accelerator NW, and we expect to receive the support of the institutional support of das Land NRW. And we are also applying for an accelerator program in Abu Dhabi. It's the GOTANS Accelerator Program. And that's an accelerator program we're doing through one of our American investors with whom we have had a lot of a change in the past month. That is the DCBC. And they recommended us to attend to this accelerator program. And the main reason for doing that is to achieve funding to produce the prototype. We are at the moment in the process of securing IP and checking private investors' funding sources, and then also public governmental funding. And until that is not clear, we continue by securing the IP and defining the system engineering. So that's pretty much what we're doing. We're competing for funding at innovation competitions, and we are requesting also support from local government, and also applying for funding at different entities, such as the ESA, tenders at the ESA, and also tenders at a national level. So it's not easy when you are in a startup.
Yes.
So yes, we are very confident that the technology is getting the traction that it deserves, and the issue of the funding to move into the next level is going to be solved soon.
Okay. Okay, thank you very much, Manuel and Marcus, for the presentation. There are no further questions. There is someone, the last question from Lars Kessler.
Yeah.
Henrik, would you read it?
I can, yes, you can. Okay, asking for students of aerospace engineering, do you consider to employ or accept interns for studies and practical projects? Since solar electric propulsion is a new interesting topic, this would be very interesting.
Yes, please. Feel free to contact and send us. Yeah, we have, I mean, it is important to say, Dirk, we have been writing proposals and bringing this technology since 3 years. I was doing it before on the PI solutions. And now as a neutron star systems, we're basically, you know, polishing that diamond. And it has taken a lot of time, money, and effort, but I think that we have been able to do that because we have been always had enthusiastic students. For example, Nantwin, our system engineering engineer, he's from Aachen University. He is working with us and putting a great deal of effort on supporting all of our activities. And like we have Sonia from the University of Stuttgart, who has been working with me and consulting since 3 years, and is a candidate for aerospace engineering. And we have, I mean, I have built this company with the support of charismatic young people, students, aerospace engineers, material science engineers. Without them, I wouldn't be able to make it. So yes, please get in contact with us.
Perfect. Great to hear. So I think, was it the last question now, or are there any further questions? I think no, it was.
Okay.
Yeah.
Then let me thanks again, Manuel and Marcus, for the presentation. I think it was a very interesting topic. The number of your questions and the questions themselves show that it was very interesting for all of you. So thank you very much for all the participants for participating. And before we end, let me invite you to our next Innovation2GO webinar next week. There we have Volker Sinnhoff. He's CEO of Ixotec, and he will present more topics about micro LED displays and how can you produce them cost efficient and in a larger format. So thank you
But
very
this
much
will
again.
be in German. This will be in German.
At the
Yes.
moment, it will be.
We are going to send to you also a short video of our technology in German. It's a 5 minutes video that probably we can just resend to the people. So thank you everyone, and for your attention, and for giving us this chance. Dirk, Hendrik, thank you.
Thank you very much.
Thank you, everybody.
Okay.